All right, how's everybody doing?
Good, how are you?
Good. It's Friday. Yeah.
That's good.
All right. So our schedule, where we are, challenge 2 is due today. So be sure that you're signed up for that. And if not, be sure to do it as soon as possible next week because the points go down. We'll finish up Heaps today. That won't take us very long. And then on Monday, we'll do exam 2 review, and then Wednesday will be exam 2. And so I will post the little study guide thing just like we had for exam 1. I'll post it probably this evening so that you can look at it before Monday. But Monday we will go through everything, and we will go through practice problems as well. Any problems, questions about programming challenges or exam 2? Good deal. Right. Oh yes, I will add your quizzes to Canvas very soon. I realized I had not done that yet. So don't worry if you don't see it, it's because I didn't do it. So last time we were talking about binary heaps, and specifically the two important types of binary heap, a min heap and a max heap. And if you remember, the idea is just that we have this binary tree-like structure, but rather than holding it to like a binary search tree standard, we are using a different criteria on how we organize the nodes and the data that's in this tree. And so the idea being with a min heap that we always have the minimum value of all of our nodes at the top, and with the max, we always have the max at the top. And there are some nice properties as we go down these trees where a max heap, the parent is always greater than any of its children, and in the min heap, it's just the opposite. The parent is always less than any of its children. And we talked about how rather than doing this with a linked structure, like we've done with binary search trees and we've done with linked list, we actually put this structure into a one-dimensional array because it turns out that that is the most efficient way to do this since we don't actually need to do anything other than compute these indexes in the array when we change things. And so when we're using a zero-based index on an array, as we do in most languages, you can always find the index of a node's left child by multiplying the node's index by 2 and adding 1. And if you add 2, you can get the right child. And then if you want to get the index of the parent of a node, you can take the, you can do the index of that child minus 1, divide that by 2, and always round it down. And you'll be put right at that node. And so typically we use the binary trees in a way where we know how much memory we need. We can allocate it all ahead of time. And then we don't need to store any extra data, any extra pointers, or anything like that. We can keep it all within that structure. And that kind of leads nicely into the idea of a heap sort, which is a way of sorting an array of elements. And if you want to sort them, small to large or large to small, you can use the respective min or max heap. And the great thing about that is all you have to do is keep removing elements from the heap, and they are ordered in whichever fashion, whichever type of heap it is. And so this means, combined with the idea of it being in an array, you don't need any extra storage during the sort routine. You can actually just take a chunk of unsorted elements, and you can begin to put it in a heap, and then remove it from the heap, and it will come out sorted in the same amount of space. And so that is what makes kind of this structure very convenient and very nice. So today, we're going to talk about making a heap in a slightly different way than we did last time. So last time we talked about essentially creating a heap one element at a time. So we had an empty, heap structure, and then we just had a list of elements, and we just added one, and we made sure it maintained all of those properties that it needs to, and then we added another one. And that works fine. But if you think about that, each insertion takes us log in complexity time, where n is the number of nodes in the heap. And since we have to do that for n elements, if we're adding them, that gives us an overall time of n log n. But if we do this if we have all the elements initially and they're already in an array, we can do this in a slightly shorter amount of time. So we can do this in linear time, just big O of n. So that's what we're going to do today, is walk through creating a heap from an array of existing elements. And so the idea is that we'll just take our array, our collection of these elements, and we will just declare it to be a heap, right? Because like the heap is just an array, and it's just like a way of looking at it that makes it a heap. But it's a broken heap, probably, because it probably is not ordered according to the rules of a min or a max heap. And so the idea is, once we consider it a heap, all we need to do is fix it. And the way we can do that in linear time is, what we want to do is we go, and you remember with the heap, it's always a full tree. So each level is full, except for the last level may not be full. We want to go find the first non-leaf node we want to find the one that's kind of at the end, right? So all the way to the bottom and to the right. That is a non-leaf node. So like in this simple example, these are both leaf nodes, so these would not be something we would start with. Actually, in this case, the root would be the first one, but we'll look at a bigger example. And the idea is we go to that first non-leaf node, so that first node that has the children, and then we just do that same process that we did when we would delete a node, if you remember, where we kind of went down the heap and ensured we swapped things until it all, compared correctly. And we can just do that for each of these non-leaf nodes, and then we will end up with a heap that is a valid heap. So, the main thing that we need to know to get started with this, when you think about the heap and it's stored in an array, the first non-leaf node is going to be located at so if we take the number of nodes in the full heap, divide that by 2, go ahead and take the floor of it, and subtract 1, that'll give us the index of where we need to start, always. So, and that'll be intuitive when you see this. Okay. So let's just imagine that we've got this collection of numbers here, and we're going to try to make this into a min heap, so the smallest at the top. And if we look at it initially, we can tell pretty quickly that this is not in a order that is a valid min heap, right? Because like 2 is down here and 21 is above it, a couple of others, right? So what we can do is first we need to pick where we're going to start. And so remember, we want to start with the first non-leaf node. And in this case, if we come kind of from the most recent element here, well, this is a leaf, this is a leaf. When we come up to this level, these are all leaves, right? And so 1 is the first node that we encounter that actually has children. And so that's where we start. And if you compute that index, you'll see 9 over 2, you get 4.5, so we go down to 4, and then subtract 1 to get the index, and that's 3, and so you can see that corresponds with 1. And so that will get you your starting point each time. And so we'll start there, and we'll do this you just do this in a for loop. And the first thing we do is just like what we would do when we're kind of going down and making sure things are in order, is we look to its children to see if the proper order is there. So we can ask, is 1 less than 501? Is it less than 502? And yes, it is. So there's really nothing to do for this node, right? So we'll go ahead and decrement I. So we're moving backwards at I towards 0. And so now we get I equal to 2, which puts us over here at this node. And we'll do the same thing. We're going down. And so you'll remember with a min heap, we always, when we look at the children, we choose the smallest. With the max, we always choose the largest. So the smallest child of 500 is 27. And so then we can ask the question there, is 500 less than 27? And no, it's not. So all we do is swap those. Okay? And now we have 500 down here. we need to continue checking, but it's a leaf, so it's done. There's nothing else to do there. So we can move to the next node, and that means we're just going to decrement I again. And so now I becomes 1, so we go to the node at 1, which is 2 over here. And we go through the same process. Its smallest child is 1. And so we can ask the question, is 2 less than 1? No. It's not. So we swap it. And then what we need to do is check on 2, since we've moved it down here. And is 2 less than 501? And it is. So that's fine. So now we can decrement I for the last time. And that puts us at the root node. And so the smallest child of the root node is 1. And we can ask, is 21 less than 1? It is not. And so we'll swap it, just like that. And now we'll need to do the same thing in this position. Its smallest child is 2. So we're asking, is 21 less than 2? And it is not. So we will swap that. And that will put us down here. And we'll ask that question about 501. And we'll find yes. And so at that point, we're finished. And so we've taken that structure. And so now if you look at it, you can check it is a valid min heap. And so that process is more efficient than if we were to do the same thing, adding each of those in sequence. And you can kind of think of it, it has to do with the direction we're going in this structure, going down versus up. And you can look at it with big numbers and graph it out, and you'll see that it is, in fact, the case. Okay. So does that kind of make sense? Is that intuitive? You have questions about any of that so far? All right. You ready to do a max heap? Okay. So we're going to start with the same structure, right? And we can have it in the array there. And we can look at this to see if it's a max heap, and it's definitely not because there are giant numbers at the bottom and small numbers at the top. So we will do the same thing, and because this is the same structure, right, our initial starting point is the same. We're just going to use a different criteria in the comparison. So we'll start at the node with the value 1, and we will look for its largest child in this case, which is 522. And we will ask, is 1 greater than 522? And it is not. So we will swap it. And now 1 is a leaf, so we are done with that part. And we can decrement our index and go to the next node in our list. And so that is 500. And so when we get to 500, we're going to do the same thing. We're going to look for its largest child, in this case, since it is a max heap. And we can easily see that 500 is larger than its largest child, so there's nothing to do for it. We can go ahead and move on and decrement I. And so now I is 1, which puts us at this node with 2 is the value. And its largest child is the node 522, which is larger than 2. And so we will swap those. And now we have to keep going down until we get this into a position where the condition's met or we're a leaf. And so the largest child of 2 is 501. And so that is larger than 2. So we will swap it. Now we are into the leaf position, so we can decrement I and go back to our node. And that puts us at the root node in this case. And so we can now look at its children, and the largest is 522, which is larger than 21, so we're going to swap that. We'll do the same thing once we get into this position. So now the largest child is 501, and so we will swap that. And then we'll get down here, and the largest child is 2, which is not greater than 21. So we are all done there. And now, if you look at the structure, you can see that this is put into a max heap order. So everything is, every parent is larger than its child in this case. So it's the same exact thing, just looking at a different direction on the comparison. So are there questions about that? Okay. All right, well that's it. That's heaps. And that's everything we're going to do for exam 2. Yeah, we're done for the day. So come back on Monday for the exam 2 review. And that exam will be trees, binary search trees, AVL trees, and heaps. Shouldn't be too bad. So I'll see you then.